Okay, it's great to be here. The topic of my talk is more than a specific result or a specific family of results, although we'll see a few, is a specific way of thinking on certain geometric problems. Okay, so that's why it has the word reasoning in the title. And let me just put up a slide which says, what do I mean by quantitative geometry? This will become clear by examples during the talk. Here I did something which is grammatically illegal. I use quantitative in the definition. But as you will see, these are questions where they are just empty or either trivial or too easy or just have no content unless you introduce quantitative parameters into the problem. Asymptotics, things of that form. You will see many examples. So just think about questions about finite objects. If you want to embed them somewhere infinite, usually you can always embed them, and unless you add quantitative parameters which measure how successful you are, any question that you would ask qualitatively will probably be meaningless. Okay, and same goes for, let's say, finite dimensional norm spaces. All finite dimensional norm spaces of the same dimension are isomorphic, but it becomes interesting when you start measuring quantitatively all kinds of parameters that you care as they depend on dimension. Okay, and these problems are just by nature, or many of them, not all of the things we'll see today, are really finite problems in hiding or analytic problems. So these are problems that have a lot of analysis and combinatorics in them, even though they're not stated that way. Okay. So this is a huge field, and I want to just focus today on a way of thinking about certain problems in this field, which is taking a problem which has no probability a priori in it, and solving it by just introducing a probabilistic interpretation of the question. And then you somehow see what to do, or you have all kinds of ideas that would have been strange to do if you wouldn't have interpreted what you're trying to do probabilistically. Okay, so that's the goal of what I want to do today. Okay. So just so I'll be able to start stating results, let me give the first simplest definition, which probably many of you have already seen. I just want to say how I'm going to be comparing metric spaces. We're going to be, this is just so I can state the first results. So if I have two metric spaces, x and y, and some function by Lipschitz function between them, its distortion is just the product of the Lipschitz constants. So equivalently, the distortion of a function is the smallest number d, such that, first of all, you're allowed to rescale the metric. So there is some scaling factor lambda, such that for any 2 points in the image, the distance between 2 points is, after they have been rescaled, is up to a factor capital D, what it was in the original space. So it's a very natural way to compare how metrics are similar. And the parameters that, this is just notation, we always think of y as some big spaces and x as some small space. Often it's going to be finite. And c sub y of x is defined as the smallest distortion, such that you can embed x into y. Okay, it could be infinite, and many times it will be. And I guess that apart from one or two examples, we'll only be interested in embedding into LP spaces in this case. So capital LP will be LP on whatever measure space you care about, it just as long as it's infinite. So let's say LP on the interval 0, 1, and then I'm going to write CP of x. And the parameter C2 has a name. It's called the Euclidean distortion of the metric space X. So this is the best way that you can represent X as a subset of Euclidean space without caring about dimension, just infinite dimensional Hilbert space. Okay, so this is a number which measures how far away is this abstract geometry from Euclidean geometry. Okay, so even though this is not the topic of my talk, I have to dedicate some time to the main or the most famous application of probability in geometry, which is the probabilistic method. And that's a huge field, and that's actually not what I want to discuss, to put emphasis on, but the probabilistic method is a great way to use probability to prove that that all kinds of exotic objects or special structures exist in metric spaces. And I think probably the first application of this method is a famous theorem of Dvoretzky, which says the following. So give me a number alpha, think of it as a target distortion, the error you're happy to incur. Okay, so give me a number alpha bigger than 1, let's say 1.1. There is a constant depending only on this alpha, with the property that for every n in any n-dimensional normed space, you can find a linear subspace, which is Euclidean up to this error that you were happy to incur, but its dimension is big, is at least this constant, which depends only on the error, times log n. And this is optimal. That's actually, the logarithmic dependence is very easy to see. The dependence on alpha is a major open problem in the field, and bounds are way off, upper and lower bounds. And this is an example of a probabilistic, of the classical type of probabilistic thinking in geometry. And maybe, I'm sure that many of you have seen it, but just to say a few buzzwords, what's happening here is most of the work comes into defining a special notion of random. What does random mean here? So you introduce a notion of a random k-dimension, C alpha log n dimensional subspace. So you come up with a special inner product depending on your normed space, and then random will be just uniformly random according to the measure and k-dimensional subspaces induced by this Euclidean structure. And then you show that if you choose your randomness correctly, then really a random subspace Y will work with high probability. Okay. So in the nonlinear world, we have an analogous phenomenon, which actually, so what I'm stating now is the end of a long list of papers, and this end worked because we returned to this, essentially the same approach that I described for Dvoretzky's theorem. So there were previous results which were deterministic, and this is just the optimal result. So here's the statement: give me a number epsilon, let's say 0.001, then any endpoint metric space X, for any such X, you can find a subspace Y, okay? It's big, okay? It has at least n to the 1 minus epsilon points, but its Euclidean distortion is just a function of epsilon, not a function of, and we'll see very soon that you cannot hope for anything, without passing to a subset, you couldn't have hoped for something of that form. So, and this is optimal as stated, except for this universal constant. It's 8 right now. I don't know what it is, but up to the constant, this is the truth. So if you want a subspace of a subset of size n to the 1 minus epsilon, the error that you're going to incur is 1 over epsilon up to constants. Okay, so, and actually I will say a few words about this. This is a non-trivial fact that you cannot do better, and it actually is proved using probabilistic arguments also. So this is what's happening in the nonlinear world. And here I want to say again that how do we use randomness in this proof, which will come back again. So again, this subset Y in the statement here is found randomly, okay? And it's done in the following way. Here is the main theorem. So it's a structural theorem. So let's see what's written here. So give me any endpoint metric space and some number alpha bigger than 1, okay? Then depending on these, then for this data, you can find a distribution. Maybe I will put up a picture so I can at the same time explain what's happening. So, so for any, then there exists a notion. This is similar to what I said about choosing the randomness in Dvoretzky's theorem. There exists a notion, a distribution over sequences of partitions of X. So pk is just, for each k is just a partition. It's a finite metric space, so it's a partition of X into finite sets. And they have the following property. They start out with a trivial partition, just the entire space, I guess. So P0 is just going to be the entire black space here. If any chunk, any element, any atom in the kth partition has diameter which increases exponentially. So next time it's going to be the red parts, and then the blue ones, and they decrease exponentially in diameter. It's a decreasing partition, so pk plus 1 is a refinement of pk. So a very useful notation is that, I guess I wrote it here, that always p of, if you have a partition of a metric space, p and a point in the metric space, then p of x is the unique element in the partition to which x belongs. Okay, so this just means that for every x, these sets decrease. And now comes number 3, and that's actually where all the work is. So what does this say? So there is this notion of randomness, which depended on the geometry of the space. I'm not telling you where it came from, but you can design it in such a way that if you take a point x in your space, then for every k, the probability, look at the following event. You have an you want that for every scale k, because these decrease exponentially, what's written here? Remember that the diameter of pk of x, the element to which x belongs, was, well, bounded from above by a diameter of x over a to the k. What I want to say here is that alpha is just a parameter. It can be 100. Okay, so I want this 1 over alpha fraction of this diameter of the set to be completely in that set. So here is x. In the beginning, it's the black partition. So, okay, that's the entire space. That's interesting. But then in the red partition, the diameter is going to be 1 over 8, and the ball of radius, whatever alpha is, 1 over alpha times 1 over 8, is going to be contained in the red piece to which x belongs. And now you pass to the blue pieces, which are smaller. So now it's this one, and now you're ensured. Now you have a 1 over 64 diameter, and the ball of the same constant fraction of that is still inside this partition. So x always feels that it is far away from the boundary. Okay, not with a big probability, with this much probability. Okay, so bounding events of this form, that the probability that for every possible scale something happens, that's where all the work is. This is a beginning of what's called a maximal inequality. This is a probability of a maximum of events. Yeah. N is always a number of points. X is an n-point metric space. Okay? So this is the statement. So you somehow design this notion of randomness, and then you finish as follows. You take a random subset, which is exactly the points x in x, for which this event happened. Okay? So it's a random subset, depending on the randomness of the partition. Each fixed point has probability n to the 1 over 16 over alpha to be inside it. So in expectation, the number of points in this random subset is n to the 1 minus 16 over alpha. And then you have to argue, it's not a hard argument, that it's a simple induction, that because you had this, for these points are always far away from the boundary, the metric actually, you can understand it and you can prove that it's Euclidean up to factor 8 alpha, whatever. So if you call 16 over alpha epsilon, then 8 alpha is like 1 over epsilon. This is exactly the theorem that I said. So, so this is an example of the probabilistic method to prove existence of objects. And we will come back to it, I hope, later. I want to say very quickly another example of the probabilistic method, which is probably more, just like Dvoretzky's theorem, the nonlinear Dvoretzky theorem has many applications in several directions. This is a very easy fact called the Johnson-Lindishaus lemma. But it is just a very, very useful thing. So what it says is that in Hilbert space, if you care only about distances, any endpoints are essentially in dimension log n. So for any number epsilon and for every number n, if you give me endpoints in Rn, in L2, you can find endpoints in some Rk, where k is log the number of points, but the pairwise distances didn't change. They changed by your 1 plus epsilon, 1 plus epsilon, 1 minus epsilon. And this is optimal both in terms of dependence on n, up to logs in dependence on epsilon. So this is just optimal. The proof of this is again a probabilistic argument, which is very easy. I can just tell you what it is. What you do is you take, so k was the target dimension you were shooting for. So essentially any random matrix will work. Let me work with Gaussians. You take an n by k, so you take Gij, these are just independent standard Gaussian random variables. I goes from 1 to n, j goes from 1 to k. This k is small, that's the target dimension you're shooting for. You look at the random matrix, which is this object normalized appropriately, and your y's are just going to be these random images under the random matrix. And you just argue that the bad event, this is the probability that you're off by more than a factor of 1 plus epsilon. This is just a very easy argument. It is an exponential decay of this type, and what we wanted is to ensure n choose 2 conditions for all pairs. So you do the computation and you see that you can succeed with high probability when k is like 1 over epsilon squared log n. So that is a very easy fact. We know it's very powerful. But this is just another, so all the random argument that I showed before, both for Dvoretzky and the nonlinear Dvoretzky, give tight results. Even this one gives something close to a tight result. So the questions in the Johnson-Lindishaus lemma or in this dimension reduction phenomenon, essentially any question that you might ask is open. There are really many fascinating open questions in the field. But recently, at least in the way it's stated, it turns out that this characterizes Hilbert space, essentially among normed spaces. So here's a statement of a very recent theorem. So give me any normed, think of it as infinite dimensional, there are finite dimensional versions. So give me any infinite dimensional normed space, X. And assume that there are 2 constants, let's say k is 10 and d is 2. They're numbers, okay? There are 2 constants for which the Johnson-Lindishaus lemma is correct. So in the space X, so for any n points in X, you can find a little k-dimensional subspace Y and a linear mapping T. So before it was not only a linear map, it wasn't only existence of a mapping, but it was with high probability over mappings. So now we just want exists one linear mapping such that in the image, the distance between T of xi and T of xj is a distance between xi and xj up to your factor d, let's say 100 or 100 million or whatever number you prefer. And the dimension is k log n. So all I'm saying is if I have some norm, let's say in LP space, you might hope that you can do this same thing in some other LP space. I have some norm for which any endpoints can be embedded via linear mapping into a log n dimensional subspace of the same norm. So this implies right away that you're ridiculously close to Hilbert space. In the following sense, any n-dimensional subspace, Z of your space, embeds into Euclidean space up to constant to the log star n, where log star is the inverse of the tower function. So log star of n is the number of times you need to take log to get a constant. This is a ridiculously slowly growing function. So actually, the key point here, and there is some work involved in showing the assumptions are just about dimension. There is no Euclidean structure appearing anywhere. And from this existence of a mapping, you have to come up with a scalar product up to these log stars. So there is some way to do it. You use a lot of machinery from Banach space theory. But the surprising thing is that you cannot, so it seems like an artifact of the proof that we get something tending to infinity very slowly, we're doing something wrong. but that's not true. We can construct an infinite dimensional norm space which satisfies these statements. So it is true, it satisfies Johnson-Lindau. Any endpoints in it embed into a log n dimensional subspace of it with factor 2. You can do 1 plus epsilon if you want. But it has bad subspaces whose distortion does tend to infinity with n, but it's again the ridiculous range, but it tends to infinity. That we can get 2 to the inverse of the Ackermann function from log, which is much slower than log star. So if you don't care about these functions, and I don't, it essentially says that this random approach is the best thing you can do in normed spaces, unless you're really, you really care about something like inverse of the Ackermann functions. Okay, so this is something very recent. What? Yeah, it's separable, it's reflexive, it's uniformly convex. Yeah. Whatever nice property you want of it, it has. Okay. For example, it must be ridiculously close to Hilbert space by the first statement. There are these bad subspaces for which you get 2 to the inverse Ackermann, but you can use the first part of the theorem to show that all subspaces are very close to L2. So these spaces up to these log stars, it really looks like L2 everywhere, but there is a little wiggle room. Okay, that's it. So such closest to L2 implies automatically, let's, for example, that it has an equivalent uniformly convex norm. This is work of Pizier, so just the statement itself. Okay, so that was actually, so these were examples of using probability to show that things exist. This is well known, this has been studied a lot. What I want to show you now is all kinds of completely different arguments where I'm not proving that something exists, I'm proving deterministic statements, I'm about that certain geometries fit or don't fit in other geometries. And the way I solve these problems is by interpreting them probabilistically, not by showing that something exists probabilistically. So this is so I want to start with a theorem that my hunch is that many of you have seen it. It's a very famous theorem. It's a beautiful theorem of Bourgain from 1985, which says that for any n, any endpoint metric space X embeds into Hilbert space with distortion log n. And I don't know if you can see what's on the bottom here. This is optimal. So Bourgain proved this up to log-logs, and then this was proved by Linear London and Rabinovich later that this is optimal. So many people quote this theorem. It's a famous theorem, and I thought this is actually a good opportunity because there are so many mathematicians here from different fields that I'll actually show you the proof. So I just want to show you the proof of Bourgain's theorem, and I want to show you what ideas go into it. So here's the formula for the embedding. It's a closed formula. So let's just see what this says. So I'm just going to show you the proof. So k is going to be roughly log n, okay? From now on. And the embedding is going to be to embed every point in my n-point metric space X into R of the Euclidean space of dimension 2 to the n. It's going to be indexed by all subsets of your metric space X. And for every subset, I have to give you what the coordinate corresponding to this subset is. And here it is. You take a point X, you look at the coordinate corresponding to the subset. This is what I denote by fx sub a. And it's this number, some normalization, which we need to understand what it is, times the distance from X to the set. Okay, so that's a formula. Okay, you write this in each coordinate. And the theorem is that distortion of this concrete embedding is log n, independently of the metric space that you started out with. Okay, so so that's Bourgain's theorem. But nobody can, so you can prove this theorem just using formulas, and actually that's the way Bourgain does it. But of course he came up with it somehow. So here is, I want to discuss what does f mean. Okay, so I gave you a formula, let's see what it means. Okay, and then when we see what it means, it's going to be very easy to understand where this log comes from. Okay? Okay, so here's just notation. If I have a subset A of my metric space X, I'll denote by pi sub j of a to be this weight that appeared over there. This is the following thing. It's the probability. So take a random subset of your metric space X, which is chosen the following way. For every point in the space, decide if it's in your random subset with probability 2 to the minus j, and independently for different points. So this is just a probability that after you did this operation, you saw the set you got happens to be A. Okay, now the point is, now K, remember, was roughly log n, so what alpha sub A is the average such probability as this 2 to the minus j runs from 1 to roughly 1 over n. Okay, so I average these probabilities, and then with this notation, here is the embedding. So I take root of this average probability over all possible densities of these sets. I'll call this 2 to the minus j the density of the random subset, for obvious reasons. So this is just the same formula, okay? So let's right away make the following observation. Where's j? It's a sum over it. Who's asking? I can't see. Okay. Oh, the meaning of the number j, 2 to the minus j is the probability that a point is in the random subset. Okay, but I'm running over all possible probabilities. So j runs from 0 to log n. So 2 to the minus j runs from 1 to 1 over n. Okay, so I look at a family of random subsets. But each one, the randomness is, each point is, it's rarer, they become sparser and sparser. Okay, but j is just an index of summation. It will mean the probability that a point is in the set, or 2 to the j is that. Okay. Okay, so first of all, just because we wrote it this way, but that's obvious, the sum of these weights is 1, which just gives you trivially that the mapping capital F is a Lipschitz function. Just because you write what it means to be distance from fx to fy in L2 norm squared is the sum of all indices. Here we had root of alpha a, so it becomes alpha a times the difference of distances from the set. Distance from a set is a Lipschitz function with constant 1, and the sum of the alphas is 1. So that's not the issue. The issue is to bound the distance from fx and fy from below. Okay? So just for notation, a sub j is always going to be the random variable, which is actually a random subset of your set. Each point is in the set with probability 2 to the minus j, and all the points are independent. This is happening, these selections are independent of each other. So the whole point is, why is this big? Okay, and so here is the reason. So forget for the moment there is, just to be correct, I have to do some truncation, but forget for the moment about this first line. Here's a number, r sub j. So I fix from now on 2 points in your metric space, x and y, and I want to show that the distance from fx to fy in L2 is big. So for these fixed 2 points, I'll denote r sub j to be the smallest radius such that x, in the ball around x of radius r, there are at least 2 to the j points. And at the same time, at the ball around y at radius r, there are at least 2 to the j points. So here, this is x and this is y. Rj is the smallest r, such that in the orange ball and in the green ball, these are the same radii, you see at least 2 to the j points in your metric space. So I grow a ball until I see enough points there. And actually, I will want to truncate it. So I actually, Rj twiddle is going to be the minimum of Rj and the distance from x over y over 4. This is just so that these balls are always going to be disjoint from each other. It's going to come in the argument. But this is just a technicality. You can ignore it for now. So balls, by the way, from now on are going to be closed. So bxr is with a lesser equal r, and b with a circle on the top is going to be the open ball in the rest of the argument. So for this pair of points, I chose 2 subspaces and the key, 2 radii, a sequence of radii. And the key fact is that the probability, so Aj is this random subset each point is in with probability 2 to the minus j, the probability that if you measure the distance from x to this random subset and the distance from y to this random subsets, these numbers are at least the increment of the different radii, this probability is just some constant. I wrote 1/12, but it's a universal constant. That's the only thing that matters. So this is very easy, but this probabilistic interpretation really shows why this is easy. This is why. So let's just see what the definitions are. Rj was the smallest radius, so that in these balls you get at least 2 to the j points.
This is for a
X and y are fixed.
you haven't yet added.
I'm fixing over j. Yeah, I'm fixing j. Yeah, the probability just on 1j. Okay, so where was I? So Rj was the smallest radius such that in the closed ball you see at least 2 to the j points. So by the definition, in the open ball, either around x or around y, there is less, strictly less than 2 to the j points. That's how Rj was defined. So this is by symmetry. Let's just assume that x is this point. Okay, so in the open ball around x, there is less than 2 to the j points. We know that. Now observe that this event that's appearing in the probability star we're going to be happy if this random subset has a point in the ball of radius rj minus 1, but does not have a point in the ball of radius rj. Because then the distance from x to aj will be less than rj minus 1 and bigger than rj. And that's exactly what I want to get here. Okay, so that's when we're happy. But now, because these two balls were independent, I can compute this probability. I'm looking at the probability, the event that the random subset intersects the ball of radius rj minus 1, but does not intersect the ball of radius rj. That's by the definition of the probability, because these are, when the two sets are disjoint, these are independent events. So I get it's the product of the probabilities. You can write down exactly what they are. It depends on the number of points. But you know that in this small ball, there is, by definition of rj minus 1, there is at least 2 to the j minus 1 points. And in the big ball, there is at most 2 to the j points. This is how we chose x. And this product is just a constant. Okay, so that's the fact. But this finishes everything, this fact, because then you just do the computation. You interpret what's going on here probabilistically. You look at the distance from fx to fy. I just wrote down what it is. Now remember, alpha a was the average of this pi j of a. Pi j of a was the probability that that a sub j equals a. That was the definition of it. So this average of these probabilities. So this distance is just the average of the expectation with respect to the set aj of the distance between 2 points. The distance from x to aj and the distance from y to aj. And we just proved that with constant probability, universal constant, this distance here inside the expectation is at least the increment of the radii. Okay, so with constant probability, we gain this distance. So the lower bound, we have this 1 over k times the sum of the increments, and now you can do Cauchy-Schwarz and telescope, and you just get what you get. You get exactly the lower bound. So that's Bourgain's theorem. Okay, so this is an example, very early and the simplest example, but a clever example of how you can use probability to prove something that has no probability in it. This is a statement about a general metric space embedding into L2. You don't prove, I'm not giving you a distribution over embeddings and just telling them one of them works. I'm just giving a formula which has an interpretation. And this interpretation leads you to prove the theorem. Yeah, so.
Where did these averages come from?
Well, I can only get rj minus 1 minus rj. I showed you that if I take a fixed j, for every pair of points, I get rj minus 1 minus rj with constant probability. Okay, but I need, by Lipschitz, I need to get at least the distance from x to y up to a small factor of as possible. So when I sum over all of them, it just telescopes, and the last one is a distance from x to y. Okay, that's a. You don't know where the action will happen, but the sum will save you. Okay, that's a. Okay, so I want to change to a different topic. I want to discuss another situation where, again, we want to studying things quantitatively is the only way to go. So, and the situation is that we're already in a bad situation. I'm giving you some infinite metric space, and I tell you it's not Euclidean, the distortion in L2, it doesn't embed by Lipschitz into Hilbert space. Can I still say something interesting about such geometries, which are essentially anything we care about is of that form? So how can we quantify, or can we measure how much a metric space X is non-Euclidean if we know that it's non-Euclidean, that the entire space doesn't embed by Lipschitz? So there is the obvious, actually the classical suggestion that what people have been doing for years is, we'll say, okay, the entire space doesn't embed into Hilbert space, so let's run over all possible endpoints in the space, look which one is the most non-Euclidean, and call this sequence AN. AN must tend to infinity, that's a simple compactness argument. And you can ask, what is the rate at which it goes to infinity? That's a very natural way to measure how non-Euclidean a space which is already not in Hilbert space is. So this is very natural. Unfortunately, there are very few situations where we can answer this question because it's difficult to somehow find the worst and the endpoint subset of some big infinite object. Let me give you a few examples and maybe mention an open question or two. So for subsets of L1, this is the truth. So so here's just the theorem is that if you give me any endpoint subset of L1, you can embed it into L2 with up to powers of log root log. So the root log is, the fact that this is the correct power of log, this is due to Enflo from 1969. And this embedding it's a more involved argument, but similar to what Bourgain did. So you give some sort of concrete embedding and you analyze it probabilistically. So the argument you have seen, that's the philosophy that's hiding behind it, behind such a theorem. And I can say right away that that's it. We don't know anything about any other interesting Banach space. So clearly, so L1, we essentially solved it up to these logs. L infinity is arbitrary metric spaces. That's not interesting. L2 is not interesting because it's already in L2. What about any other LP space? We just don't know any theorem of this type. Okay, we can give some bounds, which are far from optimal. And so this problem of looking at the worst endpoint subset is actually not so easy. Let me just say a couple more examples that we can say something about. So we know how to deal with metric spaces which are low dimensional. They're doubling. I don't want to define it right now. You can ignore it if you want. But for example, if your metric space is any Riemannian surface of bounded genus, then you can improve Bourgain's theorem from log n to root log n. This is due to Rao. There is a more general embedding technique, which is again going along the Bourgain philosophy called measure descent that was developed by these authors. And what it did, it got, in many cases, optimal dependence on the hidden parameters. So the doubling constant or the genus. I didn't write what the dependence on the genus is. Things of that form. And just another example which goes in a different direction, you can ask the same question, for example, about hyperbolic plane. Among all endpoints in hyperbolic plane, which is the one which is the most non-Euclidean? Very simple question. So it turns out that any endpoints in hyperbolic plane can be embedded into L2 with distortion root log the number of points. It's much better than Bourgain, and this is optimal. Okay, so, and I think I just put up all the known examples of where we actually know how to compute the sequence AN, the rate of explosion. So what I want to do is I want to discuss a completely different approach, which is to study something called compression exponents. And this, I think it was first suggested by Gromov. I will show in a second the first theorems on this topic. So, and even though it doesn't necessarily have to do with finitely generated groups, I want to restrict to it because it will simplify some of what I say. So from now on, G is going to be an infinite finally generated group. I'm going to be fixing some set of generators, finite symmetric set of generators. There's an associated word metric that's always going to be fixed. A priori, it's going to seem like the theorems and the definitions I'm going to give are going to depend on the set, but they're always not going to, they'll turn out to be independent of these choices. Okay, so you can think of these as fixed. The set is fixed and the metric is fixed. Okay, so if we know that the Euclidean distortion is infinity, which by the way, this is really essentially all the infinite groups that we know of. There is no known group which isn't virtually abelian, doesn't have an abelian subgroup of finite index for which the Euclidean distortion is finite, known to be finite. So anything that you care about, these are non-Euclidean objects, groups with word metrics. So when they're non-Euclidean, how can you still say something interesting about it? So here's a suggestion. Let's define a number. We'll associate a number to every group. We'll call it the Hilbert compression exponent of the group. What is this number? So I'm looking at the supremum over all numbers alpha bigger than 0, such that you can find a Lipschitz function, so a function f from the group into L2, which is Lipschitz in the word metric. The minute it's Lipschitz, if there was no power alpha here, then this lower bound would be by Lipschitz, and we're assuming this is not the case. Okay, so I'll define the compression exponent as the biggest alpha such that you can do this in such a way that in the image, the distance from fx to fy is at least the word distance between these two group elements raised to as big a power as you can get. 1/2, some number. Okay, so this is the compression exponent of the group. So let's denote this supremum by alpha star, alpha 2 star. You can do the same thing in LP spaces, and we'll get to it in a second. It will be convenient, and you will see later, there is also an analogous notion of which is equivariant compression. So because it's group, we have all these, it's a group, we have all these symmetries, we can take the definition that's written over here and just define the same thing, but if we demand that the embeddings are equivariant. So they are just the orbit of some fixed vector in L2 under some action by affine isometries. Okay, so, and then you can ask what is the best exponent you can get for equivariant mappings, and we'll get to it in a second. But this is just taking this definition and restricting to these functions which have the right symmetries. And the same thing goes for LP spaces. We can just change the L2 over there in the definition to LP. That doesn't change anything. So these are just the concepts I want to discuss. So yeah, as I said, this number, so it's a number. For every group I give a number, it's really an algebraic invariant. It doesn't depend at all on the set of generators. And it has a lot of information. So here's just one example. There are more theorems of this type. Guntner and Kaminker proved, I think in 2002, that if you know that the equivariant compression of a group is strictly bigger than 1/2, then it's amenable. Okay, so knowing that you can embed with a little bit better than 1/2 makes the group amenable. I prefer later, okay? I'm not going to use amenability. So for those who know, it's some algebraic property that is useful for the group. I'm not using it at all, except for mentioning this theorem. Okay, so who asked? There. Okay, so I will ask. Can you ask this question in the questions part, and I'll remind you. Okay. I'm not going to use it. Okay. So there is some interesting algebraic property that follows from this embedding problem. Okay, but I'm just gonna. I said I won't mention it again. Only on this slide I'm going to mention. So Gromov proved that for amenable groups, these two notions are really the same. So if you look at the best possible embedding into Hilbert space, the one that gives the compression, you can ensure that it's equivariant. Okay, so for amenable groups, there is an averaging argument which shows you that these questions are really about equivariant mappings. You can look at mappings which preserve the symmetries of the problem.
Are you saying these actually exist, or these
They exist. So for every alpha, well, no, the alpha itself can be a soup. But for every alpha, if you have a nonlinear, non-equivariant embedding with compression alpha, you can change it, not by a soup, to change it to get an equivariant embedding with the same alpha. Okay? So that actually used a lot of properties of Hilbert space. We needed very recently similar results for LP spaces. I don't really know how to use the Gromov's proof, but there is a different argument which shows that the same is true for LP spaces. So even for embeddings into LP spaces, you can assume that the function is just an equivariant embedding. And that's actually very useful. You're going to see in a second. So just so you'll know that this is not always true, I'm just telling you that that's easy. Actually, that's an exercise that for the free group, so that's a non-amenable group, the regular compression, just if you allow any mapping, is 1, but the equivariant compression is 1/2. So the numbers are different without some assumption of the group. So the question that I want to discuss is how can we compute this number? So it's very nice. We associate a number to every group. It's some invariant. We want to say something about it. How can we compute it? So it turns out that, again, similar to what I said before, there are very few methods known, and really new ideas are needed. And I just want to, so there are some methods. I want to show you now a method that I developed recently with Tim Austin and Yuval Perez. And I'm gonna, instead of stating it in full generality, I wanna restrict to a simple group, which is the Lamplighter group over the integers, as an example. Okay, so as a set, Z Reth Z, it's the Reth product of the integers with itself. As a set, it's the following. It's all the pairs of an integer and the function from the integers to itself, which has finite support. So this is, as a set, this is what the group is. I didn't say what the group operation is yet. So before telling you, actually I don't need the group operation. I'll tell you what it is. I need to tell you what the metric on this object is. So, so here are 2 elements in the group. What is an element of the group? It's a finitely supported function. So I wrote this above the integers. These lines are the integers. So here is the function. And there is also another number k. Think of it as a pointer or a location of the lamplighter. So here the pointer is sitting. So this is the k and the f. F is what's above, and the arrow is the pointer. And here is just another thing of this form. The pointer is here, and here is the function. It's all finitely supported. And now I'm saying, on a configuration like this, there are allowable movements, which are just the generators of the group, which is an allowable movement is either you can take your pointer and move it to the right or to the left by 1, or wherever the pointer is pointing, you can change the value that's written here by plus or minus 1. These are my allowable movements, okay? And the distance between 2 such configurations is the minimum number of allowable movements which transfer one to the other. And because I'm just caring about distance, I don't really need to define the group metric. I'll put it up in the next slide. But this is the metric. And I'm really stating a very simple case because it's one-dimensional. You can do, for example, the same things in a 3-dimensional grid or a 2-dimensional grid. And then these minimum number of operations are going to involve shortest traveling salesman tours. And actually, we know to say a lot about them, but they are more complicated. So there is the group operation. We don't need it. We won't use the group operation. But the theorem I want to say is that this number, this alpha star, this Hilbert compression exponent for this very simple object is already interesting. It's equal 2/3. Okay, so by that I mean this metric, the distance between any 2 such configurations, there is no way to put it in Hilbert space in a Lipschitz way, such that the distance in the image is bigger than a power of 2/3 of the original distance, and you can achieve this 2/3. So I want to prove this theorem. Actually, I'm going to prove just the upper bound, the impossibility result, the fact that there is no embedding that does better than 2/3. The lower bound is it's a concrete embedding that I will say something about it in a sec. Okay, so you start with the following lemma. Again, maybe many of you have seen it or know it. It's related to all kinds of concepts from nonlinear Banach space theory, which I just won't define. I'll just state it as a lemma. So it's a lemma with Markov chains. And it says the following. So you have, look at the numbers, let ZT, T is some discrete index from going indexed by the integers. It's a Markov chain and the numbers 1 to n. Okay, so the states are 1 to n. And it's a symmetric Markov chain in the sense that I start with a stationary distribution. So I start uniformly on these endpoints. And I go from I to j with probability aij, which is symmetric. Okay, that's what a symmetric Markov chain is. So for any such Markov chain, no matter how then for every t and for every function from the states, which I just called them 1 to n, into Hilbert space, the following inequality holds true. So what I look here is I run this Markov chain t steps. So Z0 is uniformly random on the points. I choose one point, run it t steps. I look how far I got, Euclidean distance squared. That's at most t times the expected single step. Okay? So once you believe this fact, it's just a simple spectral argument. We're still in L2, so actually everything is easy. I made a slide with a proof, but it's an exercise. I will not show it. This is a quadratic inequality in Hilbert space. Expand the squares. It just reduces to the fact that some matrix is positive semi-definite, and you just check and it works. Okay, there is no magic happening there. You just have to believe that it's true. But what it says is that no matter, we know this, for example, for, let's say, the random walk on the integers. After t steps, we're root t away from where we started. But any symmetric Markov chain has this property in this sense. No matter how you choose a symmetric matrix, after t steps, you will be less than root t away from where you started. So why is the compression of z with z less than 2/3? Okay? So this is a simple geometric problem. We're going to use probability to solve it. So let's take an embedding, which is Lipschitz. I can always normalize the Lipschitz constant to be 1. And the distance in the image is at least the distance to the power alpha. And my goal is to show that alpha cannot be more than 2/3. Okay? So, so what you do is you let Wt be the standard random walk on z with z, starting it. So the identity is just the 0 function and the pointer at 0. So if at time t I'm here, then I flip a coin if I'm going to go right or left. Okay? So essentially with probability 1/4, I move the pointer right or left, or I increment or decrement wherever the pointer was with equal probability by +1 or -1. So I start at 0. Let's say first step I moved here, and then I changed this 1 to 2, this 0 to 1, and slowly I walk around these objects. Okay, this is the standard random walk on this object. Is it clear what I'm looking at? So now let's just look at what happens after t steps. So the pointer is performing a random walk on the line. Half of the time, the pointer is moving on these integers. Okay, so it's performing a standard random walk on the integers. So half of the time, it's doing a random walk. So a typical picture will be that all the action is happening between minus root t and root t. Okay? Now you need to argue, it's an easy argument, that at every fixed location, it stayed roughly the same amount of time. So if there are root t locations and the total number of time was t, then at each location it stayed root t time. Again, up to constants. I'm ignoring constants. Okay. So the vertical distance, the mess that I will leave at the vertical distances, in the vertical distances I'm still doing a random walk. Right? That's exactly what I'm doing. I'm incrementing or decrementing by ±1. So the vertical distances are going to be plus minus the time, root of the time. So what is the distance from the identity of such an object? So we have root t locations, and this is up to constants. And in each one you have root of root t, it's t to the 3/4. Okay? But now you can take your function f, which was the embedding, and write down this inequality of Keith-Ball for that image, for the image of that function. So you know that the image of f of wt minus f of 0 is less than t times the expected single step. The Lipschitz condition just gives you that this term is t, because the distance from w1 to w is 1. This is a distance 1 in the group. And the lower bound is going to be, I'm going to use exactly what's written there, constant times the distance from x, y to the alpha. And then this argument, you can just check that it works in expectation with high probability. You get t to the 2 alpha times this 3/4. So as t goes to infinity, you get exactly what we wanted. This is what this simplifies to give. Okay, so that's the upper bound, and the lower bound is a concrete embedding that I don't have time to show you. I want to say a few words about what happens in LP. So in LP, this is how the formula extends. If p is between 1 and 2, it's p over 2p minus 1, which is exactly 2/3 when p is 2. I want to say, so you do something very similar, but you make the random walk more interesting. So you adapt the random walk to the space you're trying to embed in. So this is this strange thing, this p over 2p minus 1 is in the exponent. That's the optimal, the sharp exponent for this embedding of this group into LP. So what you do is, you first need to prove Ball's lemma for LP, and it turns out to be this. Because p is less than 2, you have the same thing, you just replace wherever you saw 2 before by p. That works. When p is more than 2, it's much more complicated and it's not true anymore. And I probably will have a minute to say something about that. So, but what you do now is you do, instead of this standard random walk, you do a stable random walk. So you take, so what you do here is the following. I allow jumps which are really very far away, okay? So assume that I was at time t. I started 0 as before. Assume that I was at time t, okay? And then what I do is I take a random variable, g sub t, which is a symmetric p-stable random variable. Its Fourier transform is given by this. So, and then I flip a coin if I'm going to go vertically or horizontally. So in up or down, but the amount I'm going to change is by this stable random variable. So I'm allowing a jump which is very far away. Okay? P is less than 2. Everywhere, P is less than 2. I mean, okay? The formula is true for P less than 2. Everything is less than 2. Okay? So, so now you can do the same computation and it works. So you see that after t steps, the horizontal movements got you to plus minus t to the 1 over p. In each of the locations in the middle, you stayed roughly the same time, which was t to the 1 minus 1 over p. And this became 1 over p. And then when you plug it all in, it works. So you just do this inequality, you get some strange exponents, and it works. And the amazing thing is that we can come up with embeddings which match these crazy exponents. And one of the mysteries currently of the field, which I really think is an important mystery, is that this is happening a lot, that we have all kinds of these probabilistic arguments which give optimal exponents, but the reason we know they're optimal is because we step back, we forget about all of the probability, we guess a certain embedding, and the numbers match. And we don't really know how to relate the fact that the probability argument ended at p over 2p minus 1 with the embedding that we got. So I think there is something deeper going on. Somehow, how can we use random walks to actually, how can we use bad random walks to embed groups into Hilbert space? And we don't know how to do this. So currently we have a lot of bounds which seem to be amazing coincidences with interesting numbers which just match. Okay, but I just want to say one short word is that what I just showed you now isn't correct. Okay, this isn't a precise argument because I was doing something I was starting at the identity of an infinite group and performing a random walk. But this inequality this inequality of Keith Ball is just not true in this situation. You can give many examples. It really assumed that you have a finite object and you start uniformly on this finite object and all the random walk is happening on this finite object. Okay, so I need to do something, okay, because this argument is not true. So there are two ways of doing it. Each one leads to two kinds of different directions. So this is, again, for those who know what amenable is, you can do a finite version of this, which is you can do a random walk when you start with a uniformly random point and a big enough Fallner set, and adapt the random walks so that whenever you hit the boundary of the Fallner set, you do something appropriate, and you can actually fix it. Okay, so there are versions, finite versions of this for amenable groups. Perhaps the more meaningful one, which is powerful in other situations, is actually use the fact that we can look at equivariant mappings. Okay, so Gromov, or for the L2 case, but for LP, we also know how to do this. We know that the worst possible embedding is equivariant. So it's of the form, there is some fixed vector in Hilbert space, and f of x is pi of x times v, where pi is an action of the group by affine isometries. Okay? So any such thing is of the form pi of x times v is tau of x times v plus rho of x, where tau is a unitary representation, and rho is a cocycle. Okay, so it satisfies this identity. So now that should be tau here. The term, the unitary part, is just a bounded term, right? This is a unitary transformation applied to a fixed vector, it's bounded. And I'm looking at the rate of explosion at infinity, the distance to the power alpha. So it's all about what kind of compressions can I get for the cocycle. The bounded term doesn't change anything. We're talking about asymptotics as things go to infinity. And then you just check that that Keith-Ball's inequality is true for cocycles. Okay, so this cocycle identity introduces some martingale structure on the Markov chain, and you can use other probabilistic arguments to actually prove Ball's inequality, not for functions and infinite groups, which are cocycles. Okay, so and that is actually there are much more complicated situations where we use this method, where we actually need to do this approach. Okay, so I guess I will, how much time do I have left? 0? 0. -4. So can I take back what I just said? Or, no, I don't know. Can I take 1 minute? Yeah. So I want to say that this was just a glimpse into, I really had, there are many more, actually very different arguments of this type, which start with a problem in geometry and somehow introduce probabilistic questions to solve them. In the context of these Markov chains, the original application, the reason Keith-Ball started looking at these was for classical problems called the Lipschitz extension problem, which was the problem of you're given a metric space and you're giving some arbitrary subset, some strange cloud in it. You have a Lipschitz function from it into some other metric space, and you want to extend it in to the entire space such that it remains Lipschitz. Okay, so this kind of a problem is just used all over the place in embedding theory. Many times you need to extend functions from Lipschitz data, and these Markov chains were originally appearing in extension problems. And they lead to solutions of long-standing problems in that field using the Markov chains approach. So I should just, this actually started from a completely different direction. There are also a lot of applications to discrete questions. Let me just, for example, here is a very simple one. This is actually, it's funny, I managed to talk about this. This is a result from 202 that I managed to talk about only once, even though it's my favorite application of Markov chains, just because it takes too long. And now I have negative time. But it's a very nice question, and it's amazing that I don't really know of a simple argument for it. So you look at essentially the simplest object that you have. You look at 0, 1 to the n, the usual Hamming cube. The distance is the L1 distance, so the distance between two vectors is the number of coordinates where they're different. And I tell you, I have some subset of it, but it's Euclidean up to factor 100, okay? Can it be big? Okay, so N-flow proved in 69 that the entire cube requires root the dimension distortion. So now I give you some cloud, and actually, if you think about it, this random walk argument lemma that in a Hilbert space that I said just proves it. Do the standard random walk on the cube and it works. It gives you this root n. What happens if now you have a subset which is some crazy subset of the cube? You don't know anything about its structure. And the only thing you know about it is that it's big. Can you prove that then the metric inherited from this nice product metric, the L1, the Hamming cube, can you prove that this metric is highly non-Euclidean? And the theorem is yes, and you can get up to logs tight bound. So if the distortion is d, then the number of points in x is the number of points in the cube, 2 to the n, times 1 minus a constant over d squared, and that's optimal up to logs. And the way you do it is really, this is really a designing a Markov chain depending on the space. So you really look at this space and you look at what's going on there, and you come up in the end with some Markov chain which jumps not between edges, between all kinds of clusters in the space according to special probabilities depending on the geometry of the space, and you can actually get the tight bounds using this. So that's an example of how you really, before we were looking at stable walks, so we were choosing a Markov chain based on the target space we're trying to embed into. And here, the geometry itself that we're trying to embed induces some special Markov chains. Okay, I think I'll stop here. I did not do justice to applications to harmonic analysis where this appears all the time, and or to applications to computer science. That was on purpose this time because many people heard me talk too much about that already. And I hope that you've seen ideas of what kind of mathematics goes into these quantitative questions where all of a sudden they become questions in probability. Thanks.
I have time for, I think, 2 questions, and then Assaf can take more questions during the break. So, questions? Yes?
At the end, you constructed these embeddings that achieved the 2/3 rule. But in the earlier part, the probability theory left you with a highly non-constructed method for choosing these subspaces, for instance. Do you know something about what those subspaces are?
You mean Dvoretzky's theorem?
Yeah.
That's a well-known question. So it's open. Nobody, it depends what norm you're working with. But for L1, let's say n-dimensional L1 space, nobody knows to get exactly Dvoretzky's theorem in a deterministic way. You can get almost that result. Piotr Indyk from MIT has the best result of this type. But exactly the way as stated, the optimal results, we know that there are really, really nice sections of the octahedron which look like ellipsoids, but we don't know how to get exactly that. We can get up to n to the epsilons in deterministic embeddings. So that's definitely an issue of the beginning of the talk where probabilistic arguments don't give you explicit constructions. That's not an issue in all the rest because everything is explicit.
Yeah. One more question? Yes.
What if you think we need to know what that means? Please tell us.
Okay, so look at, for example, at z to the n, okay? And look at the number of points in a ball of radius r, okay? Look at the ball, let's say a cube of radius r. The size of its boundary, the number of points in the boundary is little o of its total volume. So an amenable group is something which has sets which behave this way. So there is a sequence of sets such that whenever you give me, let's say, any finite sub, so these are what's called Fallner sets. So give me some number epsilon. There is a sequence of sets such that if you shift and you give me fixed, let's say, 5 elements in the group, okay? So there's a huge enough ball. It's not a ball. It's some huge enough set such that if you look at all its translates by these 4 elements, and you look how many new points did you get, so you subtract from the original ball, what you get is less than epsilon fraction of the size of the original ball. Okay, I'll write this down for you in the break. But morally, it says that there exists big sets, not balls, which somehow exhaust the group, and their boundary is tiny with respect to the size of the original set. And that's what's needed for these averaging arguments.
Well, let's thank the speaker again.